The Allison V-1710 engine screamed at 3,000 revolutions per minute as First Lieutenant Boyd Wagner pushed his P-40B Warhawk into a near-vertical climb over Vigan Airfield, Philippines, December 12, 1941. 5 days into the Pacific War, Wagner had already become America's first ace, but on this sortie something was catastrophically wrong. At 18,000 feet, with a Mitsubishi A6M0 locked in his gun sight, Wagner's engine began to detonate. Not the clean, controlled combustion that turned propellers and won dogfights, but pre-ignition, the uncontrolled explosive violence that shattered pistons and cracked cylinder heads. The tachometer needle danced wildly. Cylinder head temperature spiked past 500 degrees Fahrenheit. Wagner had no choice but to abort, diving away from the zero while his engine rattled like a machine gun with broken timing. He landed at Clark Field with 2 cylinders misfiring and metal fragments suspended in his oil. The mechanics found the problem immediately. He'd been running 87 Octane aviation gasoline, standard U.S. military issue, in an engine designed for sustained high-altitude performance. The Japanese Zero that escaped had been powered by 92 Octane fuel from Borneo refineries captured just days earlier. Wagner survived. Hundreds of other American pilots would not. This wasn't an isolated incident. It was a mathematical certainty written into the periodic table itself. In December 1941, the United States Army Air Corps had 2,846 combat aircraft. Exactly 0 of them could sustain combat operations above 20,000 feet on domestically produced fuel without risking catastrophic engine failure. The British Royal Air Force, by contrast, had been flying on 100 octane fuel since May 1940, 15 months of technological advantage that had literally saved Britain during the Battle of Britain. American petroleum engineers understood the chemistry perfectly. They knew that octane rating measured a fuel's resistance to detonation under compression, that higher octane fuel allowed higher compression ratios and supercharger boost pressures, that every point of octane translated directly into horsepower and altitude performance. The Merlin engines in Spitfires generated 1470 horsepower on 100 octane British fuel. The same engine design produced barely 10,030 horsepower on 874 octane American gasoline. This wasn't a 40% performance gap. In aerial combat, it was the difference between life and death, between catching a Messerschmitt Bf 109 at 30,000 feet or watching it escape into the sun. But knowing the chemistry and actually producing 100 octane fuel at industrial scale were separated by a chasm of metallurgical impossibility. The problem wasn't the octane-boosting additives. Tetraethyl lead had been available since 1923, synthesized by Thomas Midgley Jr. at General Motors. The problem was the catalytic alkylation process required to create the high-octane base-stock hydrocarbons in the first place. Specifically, the problem was hydrofluoric acid. To convert low-value refinery gases like butylene and isobutane into high-octane alkylate, the chemical backbone of aviation gasoline, required a catalyst so corrosive, so phenomenally reactive, that it could dissolve glass, concrete, and human tissue with equal efficiency. Hydrofluoric acid, HF, with a pKa of 3.17, attacked every known structural material. It penetrated steel through microscopic grain boundaries. It formed hydrates that expanded and cracked welds. At concentrations above 70%, it became hypergolic with water, releasing heat so intense that a single drop on human skin would cause third-degree burns that penetrated to the bone, often requiring amputation. The pain was described by chemical engineers who'd experienced HF exposure as being stabbed with a red-hot knife that keeps twisting. This wasn't a substance you handled with rubber gloves and good intentions. This was a chemical weapon that happened to produce 100 octane fuel as a byproduct. The engineering challenge was almost absurd in its difficulty. To produce aviation gasoline at the volumes required for global war, the U.S. would eventually consume 20 billion gallons between 1942 and 1945. required alkylation reactors operating continuously at 35-50 degrees Fahrenheit, maintaining precise temperature control within +X+X, while circulating thousands of gallons per hour of a substance that could eat through quarter-inch steel plate in under 48 hours of contact. The reactor vessels had to be fabricated from exotic nickel alloys that in 1940 were barely available for laboratory equipment, let alone 50-foot-tall industrial towers processing 5,000 barrels per day. The heat exchangers required welding specifications so precise that a single microscopic crack would allow HF to contact cooling water, creating hydrofluoric acid vapor clouds capable of killing refinery workers half a mile downwind. The safety protocols required isolation valves that could seal in milliseconds, pressure relief systems that could vent catastrophic failures without creating toxic clouds, and emergency shutdown procedures that could freeze the entire process before acid contact exceeded critical exposure limits. In 1940, exactly one company in the world had successfully operated a hydrofluoric acid alkylation unit at commercial scale. It was Plant 5 at the Humble Oil Refinery in Baytown, Texas, and it had the production capacity to fuel approximately 400 fighter aircraft. Total, not per day. Total. The company that built that first impossible reactor would become the architect of America's chemical warfare against the Luftwaffe, though their weapon was never dropped from a bomb bay. They were the M.W. Kellogg Company of New York, and in 1940 they employed exactly 847 people, most of them welders and pipe fitters, who'd spent the Depression building petroleum crackers and distillation towers. Their chief chemical engineer was a 42-year-old MIT graduate named Robert T. Haslam, who'd written his doctoral thesis on catalytic cracking in 1926 and understood petroleum chemistry the way a concert pianist understands chord progressions. Not as academic theory, but as physical intuition developed through thousands of hours of failure. Haslam had been experimenting with hydrofluoric acid alkylation since 1938, working with patents originally developed by British chemist Jesse Dubbs and later refined by the Anglo-Iranian Oil Company. The British had cracked the octane problem first, motivated by the same military necessity that would later drive American development. In 1935, the Air Ministry had issued specification DTD-224 requiring aviation fuel capable of sustaining plus 9-pound boost pressure in supercharged Merlin engines, an impossible requirement for conventional gasoline that detonated violently above plus 3 pounds. The solution was alkylate blending, and by 1939, Britain had 6 operating HF alkylation units producing 60 million gallons annually. When France fell in June 1940 and the Battle of Britain began, every Spitfire and Hurricane that climbed to intercept the Luftwaffe was burning British 100 octane fuel, a strategic advantage as decisive as radar and as invisible as radio waves. The Americans were 3 years behind, and the gap was widening. U.S. refineries in 1940 produced 182 billion gallons of motor gasoline annually, but only 40 million gallons met $100 octane specifications, and most of that was being exported to Britain under cash and carry provisions. The Army Air Corps was projecting requirements for 500 million gallons of 100 octane fuel by 1943, assuming the U.S. entered the war. That meant building not 1 or 2 alkylation units, but 60, 80, perhaps 100, an industrial expansion unprecedented in chemical engineering history. It meant fabricating reactor vessels from nickel-molybdenum alloys that were still experimental in metallurgical laboratories. It meant fabricating reactor vessels from nickel-molybdenum alloys that were still experimental in metallurgical laboratories. It meant training thousands of chemical operators to handle a substance so dangerous that a single procedural error could kill everyone within 200 yards. It meant solving corrosion problems that had defied every material scientist in the petroleum industry. And it meant doing all of this in 18 months, because by January 1942, American intelligence estimates suggested the Wehrmacht would have operational jet fighters by 1944, and piston engines running on 87 octane fuel would be obsolete before they left the assembly line. Robert Haslam understood the stakes with crystalline clarity. On February 3, 1941, 9 months before Pearl Harbor, he stood in a conference room at the Petroleum Administration for War in Washington, D.C., and presented a proposal that would have seemed insane to anyone who hadn't spent 15 years wrestling with petroleum chemistry. He proposed building 40 HF alkylation units in 24 months, each capable of producing 15,000 barrels per day of alkylate base stock. Total construction cost $386 million in 1941, equivalent to $8.2 billion today. Total hydrofluoric acid inventory across all facilities, 47 million pounds in continuous circulation. Total potential casualties in the event of catastrophic failure, incalculable, but likely in the tens of thousands if a major release occurred near a populated area. The procurement officer from the War Department asked the obvious question, "Mr. Haslam, what happens if one of these reactors fails in, say, Baton Rouge or Los Angeles?" Haslam's answer was documented in the meeting minutes. "We design them not to fail, sir, because the alternative is losing the war." After the contract was signed on March 15, 1941, M.W. Kellogg would serve as primary contractor, with engineering support from Universal Oil Products, Standard Oil of New Jersey, and the Anglo-Iranian Oil Company, which agreed to share British alkylation patents under Lend-Lease provisions. Construction began simultaneously at 17 refinery sites across Texas, Louisiana, California, Oklahoma, and Pennsylvania. The first challenge was materials procurement. Each reactor required 340 tons of Monel alloy, a nickel-copper composite containing 67% nickel, 30% copper, and 3% iron, with corrosion-resistant specifications so tight that a variance of 0.5% in nickel content would reduce acid resistance by 40%. In 1941, total U.S. Monel production was 8,400 tons annually, and the Navy had already requisitioned 6,200 tons for submarine construction and destroyer condensers. Haslam's team needed 13,600 tons just for the first 20 reactors. The solution came from an unlikely source: the International Nickel Company of Canada, which operated the Sudbury Basin mines in Ontario, had been stockpiling refined nickel since 1938 in anticipation of war demand. They agreed to divert their entire 1941 output to alkylation reactor fabrication in exchange for guaranteed War Department contracts through 1945. By June, Monel ingots were arriving at fabrication plants in Philadelphia and Gary, Indiana, where they were forge-welded into cylindrical shells 12 feet in diameter and 48 feet tall, with wall thickness varying from 2 inches at the base to 1.25 inches at the top to account for pressure gradients. The welding specifications alone filled a 247-page manual. Every seam required X-ray inspection at 200 kilovolts penetration to detect micro cracks larger than 0.003 inches. Every weld had to be stress-relieved at 1600 degrees Fahrenheit for 14 hours, then cooled at exactly 100 degrees Fahrenheit per hour to prevent crystalline grain boundary formation that would create acid migration pathways. The welders themselves required 6 months of specialized training because Monel welding behavior was fundamentally different from steel. The metal had to be preheated to 400 degrees Fahrenheit, welded with argon-shielding gas to prevent oxidation, and post-treated with pickling solutions to remove surface contaminants. A single contaminated weld could create a corrosion cell that would penetrate the reactor wall in 6 weeks of operation, releasing thousands of gallons of hydrofluoric acid into a refinery processing volatile hydrocarbons at 800 degrees Fahrenheit. The consequences would make the Hindenburg disaster look like a stovetop accident. While the reactors were being fabricated, Haslam's engineers were solving the even more complex problem of how the alkylation process actually worked at the molecular level. The chemistry was deceptively simple on paper. Combine isobutane, CIDH10S, with butylene, CIDH10, in the presence of hydrofluoric acid catalyst, and the result was iso-octane, CIDH10, a branched-chain hydrocarbon with an octane rating of 100, but the reaction pathway was anything but simple. It proceeded through a carbocation intermediate, a positively charged carbon atom stabilized by the surrounding electron cloud, that existed for approximately 10 seconds before either forming the desired isooctane or decomposing into lower-value byproducts. The hydrofluoric acid's role was to donate a proton, He, to the butylene molecule, creating the carbocation, which then attacked the isobutane molecule, stealing a hydride ion, He, and forming a new carbon-carbon bond. The reaction released 48.2 kilocalories per mole, and that heat had to be removed continuously or the entire reactor would enter thermal runaway, boiling the hydrocarbons and creating a pressure wave that would rupture the vessel. Temperature control was the knife edge on which the entire process balanced. At 32 degrees Fahrenheit, the reaction rate slowed to commercially useless levels. Producing alkylate required 14 hours of residence time instead of 2. At 60 degrees Fahrenheit, the reaction accelerated but selectivity collapsed. Instead of forming clean isooctane, the carbocation intermediates underwent rearrangement reactions, creating a mixture of heptanes, hexanes, and polymer tars that fouled the catalyst and lowered octane ratings. The optimal temperature window was 38-42 degrees Fahrenheit, maintained within +1, 5 degrees Fahrenheit across the entire reactor volume. In a vessel processing 15,000 barrels per day, that's 630,000 gallons or 10,500 gallons per minute. Maintaining that thermal precision required heat exchanger surface area equivalent to a football field, with coolant flow rates of 50,000 gallons per minute of chilled water. The cooling system consumed 12 megawatts of power per reactor, more than the entire electrical demand of a town of 15,000 people. Multiply that by 40 reactors, and the alkylation program required the construction of 6 dedicated power plants with a combined output of 480 megawatts, roughly equivalent to the electrical generation capacity of the entire state of Nevada in 1941. The acid circulation system was perhaps the most terrifying piece of engineering ever deployed in American industry. Each reactor contained approximately 120,000 gallons of hydrofluoric acid, circulating at 8,000 gallons per minute through a closed-loop system of pumps, heat exchangers, and separation vessels. The acid served as both catalyst and reaction medium, absorbing the hydrocarbon feed at the bottom of the reactor and releasing purified alkylate at the top. But hydrofluoric acid wasn't a stable, well-behaved chemical. It absorbed water from the hydrocarbon feed. Typical refinery streams contained 5020 parts per million of water, and that water diluted the acid strength from the required 88% concentration down to levels where catalytic activity collapsed. Every 24 hours, operators had to drain 3,000 gallons of contaminated acid, distill off the water in a specialized reboiler operating at 150 degrees Fahrenheit and 40 psi, and return the concentrated acid to the reactor. This distillation process created anhydrous hydrofluoric acid vapor at concentrations lethal in under 30 seconds of exposure. The reboiler was housed in a sealed concrete bunker with 1/8-inch walls, accessed only through a pressure-locked vestibule, and monitored by closed-circuit cameras. The operators who performed acid transfers wore rubberized suits with external air supply, looking like early astronauts exploring a toxic alien planet, which, chemically speaking, they were. The safety protocols developed for HF alkylation units read like a military operations manual, because chemically these facilities were weapons platforms deployed on American soil. Every unit had a dead man switch system. An operator had to physically press a button every 60 seconds, or the entire reactor automatically initiated emergency shutdown. Every pipe flange was equipped with dual seals and intermediate pressure monitoring to detect leaks before they became releases. Every reactor had a deluge system capable of flooding the entire vessel with 100,000 gallons of water in 90 seconds, neutralizing the acid through dilution, though this created its own hazard, as the exothermic heat of dilution could flash boil the water and create a pressure surge. The emergency response protocol assumed that any HF release larger than 50 pounds would require evacuation of all personnel within a half-mile radius and notification of civil authorities. A catastrophic release, defined as more than 5,000 pounds, would require evacuation of the entire city. Engineers calculated that a worst-case failure of a fully loaded reactor, if it occurred with unfavorable wind conditions over a major city, could create a vapor cloud containing 240,000 pounds of hydrofluoric acid dispersed over 15 square miles, with lethal concentrations extending 6 miles downwind. This was not a hypothetical scenario designed to scare regulators. It was a thermodynamic certainty based on vapor pressure calculations and atmospheric dispersion modeling. The only thing preventing it was weld quality, materials science, and procedural discipline. Between March 1941 and December 1942, M.W. Kellogg constructed 41 HF alkylation units at a pace that remains unmatched in chemical engineering history. The first unit at the Humble Baytown refinery went operational on September 14, 1941, producing 13,200 barrels per day of alkylate, within specifications. The second, at Standard Oil's Baton Rouge facility, came online October 3rd. By December 7, 1941, the day of Pearl Harbor, 7 units were operational with a combined capacity of 98,000 barrels per day. By June 1942, 18 units were running. By December 1942, all 41 were in operation, producing 615,000 barrels per day of alkylate base stock, which when blended with catalytically cracked gasoline and tetraethyl lead, yielded 840,000 barrels per day of 100 octane aviation gasoline. That's 35.28 million gallons per day, 1.29 billion gallons per year, enough to fuel every combat aircraft in the U.S., British, and Soviet Air Forces combined, with surplus capacity for training operations and strategic reserves. The production statistics tell only part of the story. The real miracle was reliability. These were not laboratory-scale demonstration units babied by PhDs in white coats. These were industrial installations operated 24 hours a day, 365 days per year, by shift workers with high school educations, many of whom had been farm laborers or steel mill operators before the war. They learned to read differential pressure gauges and temperature controllers, to sample acid strength using hydrometer readings, to recognize the subtle changes in reactor sound that indicated fouling or cavitation. The training program developed by Kellogg and implemented across all 41 facilities was 16 weeks long, longer than Army basic training, and had a failure rate of 38%. This wasn't because the trainees were incompetent. It was because operating an HF alkylation unit required a level of chemical intuition and procedural discipline that most people simply didn't possess. A good operator could hear a pump bearing failing 12 hours before it seized, could smell a trace HF leak at concentrations below detector sensitivity, could feel through vibration in the metal handrails that heat exchanger flow was becoming asymmetric. This knowledge couldn't be taught from manuals. It had to be absorbed through hundreds of hours of supervised operation, learning the personality of the equipment the way a pilot learns the handling characteristics of a specific aircraft. The safety record, given the inherent hazards, was almost miraculous. Between 1941 and 1945, across all 41 HF alkylation units representing 164 reactor years of operation, there were exactly 3 fatalities directly attributable to hydrofluoric acid exposure. The first occurred at the Phillips Petroleum Plant in Borger, Texas, on July 23, 1942, when a relief valve failed and sprayed acid onto a maintenance worker who was replacing flange gaskets. He received burns over 35% of his body and died 4 days later from calcium depletion. HF chelates calcium from blood and bone, causing cardiac arrhythmia. The second fatality occurred at the Shell plant in Martinez, California, on March 8, 1943, when an operator opened a sample valve without first confirming the line was depressurized. He was exposed to acid vapor for approximately 8 seconds before his partner pulled him clear. He died from pulmonary edema. The acid dissolved his lung tissue. The third death occurred at the Sun Oil plant in Marcus Hook, Pennsylvania, on January 15, 1944, when a transfer hose ruptured during an acid concentration procedure. The operator was wearing full protective equipment, but the acid spray found a gap between his glove and sleeve cuff. He received a $4.8 million scan to guest. square inch burn on his wrist. He survived the initial injury but died 6 weeks later from infection. HF burns are nearly impossible to sterilize because the acid penetrates so deeply that surface disinfection is ineffective. 3 deaths in 4 years of operating the most dangerous chemical process ever deployed at industrial scale. By comparison, the petroleum industry in the same period lost 847 workers to refinery accidents involving fires, explosions, and hydrogen sulfide exposure. Coal mining killed 6,200 workers. Aircraft manufacturing killed 1,340. The HF alkylation program's safety record was a testament not to the forgiving nature of the chemistry. Hydrofluoric acid is fundamentally unforgiving, but to the obsessive engineering culture that M.W. Kellogg and its operating partners enforced. Every near miss was investigated as thoroughly as a fatality. Every procedural deviation resulted in immediate shutdown and retraining. Every maintenance operation was planned with the assumption that Murphy's Law was not a joke, but a thermodynamic principle. The result was a safety culture that would later become the foundation for the entire petrochemical industry's approach to hazardous materials handling. The impact on the air war was immediate and overwhelming. In May 1942, the first P-51 Mustangs, equipped with Packard-built Merlin engines, began arriving in England, powered by American 100 Octane fuel. The performance difference was startling. The Merlin V1650, 7-engine, running on 100 octane with 25 pounds boost pressure, generated 1,695 horsepower at 3,000 RPM, a 64% increase over the same engine on 87 octane fuel. That translated into a top speed of 437 miles per hour at 25,000 feet, making the P-51 the fastest operational fighter in the world. More critically, the 100 octane fuel allowed sustained combat operations at altitudes above 30,000 feet, where German interceptors running on 87 feet 4 fuel began to experience the same detonation problems that had plagued early American fighters. By 1943, the Luftwaffe had developed C3 fuel, 96-octane equivalent, but production never exceeded 15 million gallons per month, compared to American production of 1.3 billion gallons per year. The Germans were trying to fight a chemistry war with Bavarian distilleries, while the Americans were operating chemical weapons plants disguised as oil refineries. The strategic bombing campaign against Germany would have been impossible without HF alkylation. Each B-17 Flying Fortress consumed 1,700 gallons of 100 octane fuel for a maximum range mission to Berlin and back. A typical 8th Air Force raid in 1944 involved 1,200 bombers plus 800 escort fighters, consuming 3.8 million gallons of fuel per mission. The 8th Air Force flew 332 such missions between January 1943 and May 1945, consuming approximately 1.26 billion gallons of 1005-time fuel, nearly matching the total U.S. annual production capacity in 1941. Without the alkylation program, those missions would have been impossible. The B-17's Radar 1820 Cyclone engines required 100 octane fuel to maintain cruise power at bombing altitude. Running on 87 octane, they could barely climb above 18,000 feet with a full bomb load, putting them well within range of German 88mm flak that was optimized for 20,000-foot intercepts. The entire strategic bombing doctrine depended on high-altitude precision, and high altitude depended on octane rating, and octane rating depended on hydrofluoric acid alkylation. The Pacific War told the same story with even more dramatic numbers. The B-29 Superfortress, the ultimate expression of American strategic air power, was completely dependent on 100 octane fuel. Its Radar 3350 engines, the most powerful radials ever built, generated 2,200 horsepower each using 1000 octane with water methanol injection. On 87 octane, they produced barely 1,400 horsepower, insufficient to lift a fully loaded B-29 off the runway at Tinian or Saipan in the tropical heat. The firebombing of Tokyo on March 9, 1945, 334 B-29s dropping 1,665 tons of incendiaries, consumed 1.4 million gallons of 100 octane fuel. The atomic bomb missions to Hiroshima and Nagasaki each required 7,000 gallons per aircraft. The fuel that powered the Enola Gay on August 6, 1945, was synthesized from isobutane and butylene in an HF alkylation reactor at the humble Baytown refinery, catalyzed by the same acid that could dissolve human bones, cooled to 40 degrees Fahrenheit, and purified to 99.8% purity. That fuel contained approximately 114,000 BTUs per gallon, of which 18% came directly from the alkylation process. Without that 18%, the mission would have failed before it left the ground. The post-war legacy of HF alkylation is written in the fuel tanks of every aircraft flying today. Modern aviation gasoline, 100LL, the low-lead variant used in piston aircraft, still contains alkylate base stock, though the synthesis process has largely transitioned to sulfuric acid catalysis to reduce HF handling hazards. But the fundamental chemistry remains unchanged. Branched-chain isoparaffins synthesized through carbocation intermediates, producing the knock resistance that allows high compression ratios and supercharger boost. The octane rating itself, the RON/MON average that appears on every gas pump, was standardized in 1941 based on the testing protocols developed for wartime aviation fuel. The entire structure of modern petroleum refining, the catalytic crackers, the reformers, the alkylation units, was designed around the necessity of producing 100 octane fuel for World War II. The war ended in 1945. The refineries kept running, adapting their processes to peacetime demands, but the ghost of that wartime chemistry haunts every molecule of gasoline burned in a modern engine. M.W. Kellogg continued designing chemical plants until 2006, when the company was absorbed into the KBR conglomerate. Robert Haslam retired in 1955 and died in 1964. His obituary mentioning his contributions to petroleum refining in a single paragraph. The 41 HF alkylation units built between 1941 and 1942 continued operating well into the 1990s, some for more than 50 years of continuous service. The last of the original wartime reactors at the Exxon Baytown refinery, the same plant where it all started, was finally decommissioned in 2002. It had processed 280 billion gallons of hydrocarbons, produced 89 billion gallons of alkylate, and never experienced a catastrophic failure. When they cut it apart for scrap, metallurgists found the Monel alloy welds still intact, showing minimal corrosion after 6 decades of contact with one of the most aggressive chemicals known to materials science. The welders who fabricated that vessel in 1941 had done their job well. Today, approximately 30% of global gasoline production still passes through alkylation units, though most have transitioned to sulfuric acid catalysis or solid acid catalysts to eliminate HF handling. The remaining HF alkylation units, there are still 47 operating in the United States, are monitored by EPA regulations so stringent that a release of more than 100 pounds triggers federal investigation. The operators who run them are the inheritors of a safety culture forged in the crucible of wartime necessity, when getting the chemistry wrong meant not just a regulatory fine, but potentially losing the war. They understand, perhaps better than anyone, that chemistry is not an abstract science conducted in laboratories. It's a physical reality that can either power civilization or destroy it, depending entirely on the quality of the welds, the precision of the temperature control, and the discipline of the human beings who operate the equipment. The Luftwaffe never saw the chemical weapon that defeated them. It wasn't dropped from a bomb bay or fired from a cannon. It was synthesized in 41 reactors scattered across Texas and Louisiana, circulated through miles of Monel piping, cooled to 40 degrees Fahrenheit, and pumped into the fuel tanks of P-51 Mustangs and B-17 Flying Fortresses. It was octane rating 100, produced through the controlled violence of carbocation chemistry catalyzed by hydrofluoric acid. It gave American pilots a 64% horsepower advantage, a 40 miles per hour speed advantage, and a 10-10 descendant most percent Foot altitude advantage. In aerial combat, those numbers weren't statistics. They were the difference between the hunter and the hunted, between returning to base or auguring into the channel, between winning and losing the war for control of the skies over Europe. The Germans knew they were being outflown. They could see it in the performance curves of captured American fighters, measure it in the climb rates and ceiling specifications. What they never fully understood was that they weren't losing to better pilots or superior aircraft design. They were losing to better chemistry, synthesized by an industrial process so dangerous that it would have been banned in peacetime, operated by workers who risked their lives every shift to produce a fuel that most of them would never see burned. The refineries at Baytown and Baton Rouge were as critical to victory as the shipyards at Norfolk or the aircraft plants at Willow Run, but they fought their war in anonymity, behind chain-link fences and chlorine gas detectors, winning battles measured in octane points and production throughput, rather than territory captured or enemies killed. That's the deepest irony of total war. The decisive weapons are often the ones nobody sees, nobody photographs, nobody commemorates with monuments. Their industrial processes operated in the background of history, essential but invisible, dangerous but controlled, transforming base materials into strategic capability through the application of engineering discipline and chemical knowledge. Hydrofluoric acid alkylation was one such weapon. It never made headlines, it never won medals, but it won the war in the air, 1 gallon of 1004. Octane fuel at a time, synthesized through chemistry so violent it could dissolve metal, and so precise it could be controlled to within 2 degrees Fahrenheit across a 500-foot reactor tower. That's not just engineering, that's victory through applied science, and it remains the most American way of war ever devised.